As we keep learning physics and electricity, we need to know how we actually move that electricity around. And the concept in physics that allows us to move electricity is called current. Current is defined to be the flow of charge. Okay, and it has a very specific definition we can understand with an equation. I stands for current, and it's equal to the change in charge that passes some given point or goes through some given area divided by a change in time. So Q is the charge through a surface area. And T is the time that it takes to go through that surface area. Like everything in physics, current has units. The units of current are going to be equal to coulombs, the units of charge, divided by seconds, which we give a specific definition. We call this an amp. So we call it an A. A stands for ampere. Okay. So that's some basics about current. And there's one weird thing that we do with defining current. So the direction of current we consider to be where positive charges go. And this is very strange because the direction of charges should be the direction where negative charges go, because negative charges are the ones that actually move. So think about that. The direction of positive charges is the direction of current, but the direction of the charges that are actually moving are the negative charges. Okay? So kind of, if you think about it, the direction of the current that you define is actually opposite the direction of where the charges are going. Because positive charges don't flow, the negative charges actually do flow. Okay? And electrons, they don't just flow, they don't just move randomly. The electrons, they actually drift. So when electrons are flowing, they are drifting in the direction that they're moving. Okay. So if we draw a wire and we put electrons inside of this wire, these electrons are bouncing all over the place. But overall, if you add up where all the electrons are going, maybe some are moving backwards, maybe some are moving to the left. But if you add up the overall direction of all the electrons, overall, the electrons are flowing to the right. Okay? So, due to random motions, and bumping into each other and moving all sorts of different directions, the electrons aren't all moving in the same direction, but due to these random motions and bumps, electrons bumping into each other, literally bumping into each other inside of this wire, the electrons kind of flow in a specific direction. They actually drift as they're going down this wire. And we can give a definition for this. We can define this. V sub d, so V with a little subscript d, is called the drift velocity. And it's related to the current. These electrons flowing down this wire, these do represent a current, an overall current, a direction for your electrons to flow as a function of time. So we can define the drift current in terms of current, the drift velocity in terms of current, as I equals N times Q times A times V sub D. And what do all of these mean? I, we know, we just learned, is the current. A is the cross-sectional area. So that's the surface area that I'm traveling through. If I have this wire, I can imagine cutting out a little slice right here, and my electrons are flowing through this little slice. That little circle, if I were to flip this wire kind of 90 degrees so that it's pointing out towards me, is a circle. So that's the cross-sectional area that I'm flowing through. And then I have N. N is something called the free charge density. So that's how compacted in my charges are in this little area. And finally, we know Q is equal to the actual charges that are flowing. So this is how we can define the drift velocity. So how fast these electrons are kind of overall in the total, just kind of flowing, just kind of drifting down this little wire. Now we can relate current to things that we've already studied, and another concept that we'll study in a moment, something called Ohm's Law. And Ohm's Law tells us that charge flowing in a circuit depends on two things: charge flowing, current, depends on two things: voltage and resistance. So we can write an equation where V, the voltage inside of a circuit, is equal to the current times the resistance. V is voltage measured in volts. I is current measured in amps. And R is the resistance. We measure that in something called ohms. And that's basically how much electron flow is resisted. So let's talk about resistance a little bit. The resistance is actually how much a material resists electron flow. So if I think of it as being a pipe, water flowing through a pipe, resistance is how clogged your pipe is. And it can depend on the physical properties of your material. We can write an equation for resistance. R is equal to rho times L divided by A. And this is resistance inside of some wire. So we'll draw a little cylinder that has a surface area. So that's the cross-sectional area. That's the circular face of this cylinder is an area A. And this wire has a length that you travel along of length L. So the A is the area of your wire. L is the length of your wire. And then rho is something called the resistivity. Of your material. So that's intrinsic to the material itself. We see in the definition of resistance that how much a material resists electron flow is what determines your resistance, and that material property is the resistivity. This is something that you would look up in a table usually. So these are values that we've measured for different kinds of elements that you build a wire out of. And both resistance and resistivity don't just depend on the wire itself, they also depend on the temperature that they're operating within. So if you've ever had electronics, when it's cold outside, they don't work as well. That's because cold tends to increase the resistance. So if your temperature is very low, then your resistance is going to change. So we have rho the resistivity is equal to resistivity naught, which is the resistivity at some reference temperature, times 1 plus the Greek letter alpha times a change in temperature. So how different your temperature is compared to your reference temperature. And alpha is something called the temperature coefficient of resistivity. And this temperature coefficient is, again, very similar to the resistivity, where you'd go to a table in a book to find what these are. Okay, so it doesn't just affect the resistivity, which is rho, it also affects the resistance. The temperature affects resistance, according to resistance is equal to R naught, which is R at some reference temperature, some standard temperature, times 1 plus alpha times the difference from that reference temperature, where alpha again here is the temperature coefficient of resistivity. It's a very similar equation. So a good question to ask now is, who cares? Why do we care about current? Why does current matter? Well, electric current is how we transport electricity. So current leads to power. It's how you get power into all of your electronics. And there are several equations we can use to get to how power and current are related to each other. So power is equal to the current that you get times the voltage that you're producing inside of, say, your battery. And what we can do is we can start substituting things in, substituting in variables according to Ohm's Law, which tells us V equals IR. Or we can shuffle this around a little bit. We can do some basic algebra to see that I is equal to V over R. So we can use these two equations, V equals IR and I equals V over R, to substitute in for I or V in my power equation. So I can get two more equations for the power. So I can get power is equal to I times R. So what I've done here is I've taken that V equals IR and I've plugged it in for V in my P equals IV equation. So I get a new equation for power. P is equal to I squared times R. I could also plug in for the current. So I can do P equals, instead of I don't want to plug in I want to plug in I equals V over R. So I'm going to plug that in for my I. And I get P equals V over R. And I multiply that times a V. And that's going to give me another equation for power. P equals V squared over R. So now I have three equations for power. You might ask, why do I have three equations? Why do I need three equations? Which one do I use? Which one do I memorize? Well, all of them tell you the same thing. The one you will use depends on what variables you're given. And we don't have to memorize all of these. We can memorize just one of them. So I would recommend P equals IV. And as long as we know V equals IR, we can plug that in and we can substitute and derive these other two equations. There's this very powerful thing to do in physics, to be able to use equations to get other ones. So you use whichever one is most convenient. If you're struggling with that algebra, you should get some algebra practice from your teacher, from your instructor. So we have various different types of current that exist out there. There's current called AC, and there's current that's called DC. And each of these things mean two different things. AC stands for alternating current. Alternating current, it flip-flops. So we'll call this flip-flopping current. Okay, so it flip-flops up and down, it varies, but the advantage of AC is it's easy to transport and easy to manipulate. So I can change the current that I'm getting out from AC, and I can transport it very easily. Now DC, it's constant. It's called a direct current. So we know the value that it has at all times. It stays constant. But it's hard to transport and hard to manipulate. Okay, so which one are we actually going to want to use? Well, since it's easier to transport and manipulate, we're going to want to use some AC current, AC circuits. So let's talk a little bit about AC. Turns out that AC current can actually be modeled. We know how it operates. We know how it flip-flops up and down. We know that the voltage from AC circuit at any time is equal to some initial voltage of your circuit times the sine of 2 times pi times F times T, where V naught is some peak voltage. That's the highest voltage that your circuit can produce. F is something called the frequency. That's how fast your voltage is kind of flip-flopping up and down. And T is any given time that you want to know what your voltage is. So we can graph this and see what it looks like. It looks like a sine wave. We have V, and we plot it as a function of T. It's going to start at 0. It's going to go up, then back down, then up, then back down, and then back up. And it's just going to keep doing this. We can see it's flip-flopping. Now the distance between peaks is something called 2 pi f, 2 pi times the frequency. That's also, we could also call that kind of a wavelength. Okay, so the frequency, when we're talking about AC voltages, has a very common number. This frequency is typically 120 hertz. And what that means, this 120 hertz, is that means that the voltage, it flips from being up at this peak, so a maximum positive peak, to the maximum negative peak, also called a trough. It flip-flops between the top down to the bottom 120 times per second. So that frequency, that 120 hertz, means that we flip 120 times per second. So AC voltages, these are changing and flip-flopping very, very fast. 120 times per second. I can't imagine doing something 120 times in 1 second. So we don't actually see this happening. So your light isn't going to flicker if you have an AC power source, if you're running off of AC, because the power is the voltage that you're getting is flickering 120 times per second. So you don't really notice that. You're not going to see that in nature. And now when working with current, we need to be aware of some dangers. There are some dangers associated with it. And there's going to be two main dangers. One is called thermal danger. Okay? If we have too much power, if we have a whole bunch of power, and let's say our wire is clogged, something's wrong with our wire, it's having a high resistance, and we're trying to plug a lot of power, a lot of current through that. If you put too much power through an electrical circuit, that can lead to lots of resistance, and the electrons are going to back up on each other. Okay, you might feel this when you're charging your electronics. You kind of feel a wire gets warm, or your electronics actually look warm. And if you keep charging it, if you don't have regulators to stop charging, and if you keep trying to pump electrons into areas where there's not room for them, you could start an electrical fire. So this is trying to pump too much power into a circuit. You can end up with an electrical fire. We call that a thermal danger. Now, the other danger we have is the danger of shock. So this is where you would actually electrocute yourself. This would go through a person. If you send too much current through somebody and you send it through them too fast, you're going to injure that person. Okay. This can be determined. The risk of electrical shock is determined by a few different variables. Determined by your current, the path your current takes, the time that this current takes to go through you, and your AC frequency. All of these aspects can contribute to damage by electrical shock. So those are the kind of big dangers of current. And that's current in a nutshell.